How do you build a mass differential pair? You build a differential pair using two single-ended pairs. How do you do that? Take a tandem source amplifier stage. This is the input and the output. RD M1. Right? Now you mirror the same thing and bring it up in the opposite direction. This is M2. This is V out. So if this is V in plus, okay, since you have an inverting output, this becomes the negative terminal. In this case, we have V in minus. Since this is inverts, so this is going to be positive terminal. Now this is called a differential pair. Okay, or in simple terms, you can redraw it using any other way. Now in this, we will see what are the previous problems that we spoke about in the previous slide. What are they? First one is, there is no common mode defined for each other. Each one has its own common mode due to the variation. See, common mode of M1 and M2 is depending upon the RD circuits bias. So there is variation is present. And since variation is present, the bias will be different. Okay, since bias is different, this is an undesired effect. Okay, the first one. Second, what do you try to do? You have to produce a bias. So where do you put a bias? You need bias fixed. Where do you fix bias? Fix bias a place where it is going to be linear. Okay. Now, how do you make the circuit linear? You know that the source follower circuit along with the source degeneration. Source degeneration can make a circuit linear. So what do? We can add it as a following. RD, M1, M2. These are the inputs. There are the outputs. Now you do a source degeneration. So you can take a degeneration and add a current bias. Okay. So once you put a fixed current source, you get a current bias here. Along with that, this node voltage will get fixed with a common source here, right? So it is the Vs will become the common source. Now, if you look at it, let us do the analysis. Is this actually going to give? So the first theory you will use is these two devices are going to be matched. Matched devices M1 and M2. At least in theory, ensure that this is there. Second, bias the resistors in such a way that they are in saturation. Right? Ensures M1 and M2 are in saturation. What does that mean? This means that RD defines what is the VDS1 and 2 for these two MOS transistors, such that your VDS is greater than VGS minus VT, right? So that is your biasing condition. Okay, so the input will decide what is the VGS. Okay, so now you have to understand that the input is that. Now that you have a common source point here, Vs, your VGS or your VG rather than VGS your VG value has to be greater than Vs value. So there is going to be a DC component. There is going to be a DC component in VG which is equal to or greater than Vs. So there has to be a DC input. Okay. So your Vin will have a DC input for sure, and that has to be greater than equal to Vs. Okay. So that will take care. Next, what is left over? What is left over is the tail current source. So this is called tail current. The head is on the top, bottom is the tail. So that is why it is called as a tail current. And that is the solution. We'll add a tail current as a source regeneration here. And you can implement using either a resistor, or you can implement using a static current source using a NMOS device. So this will be how you will model the current source that is present. Now this will show. Now what is the behavior of this current source? The behavior of this current source will be, it has to be a constant current source. Okay. Second, you will have high output impedance. Output impedance is going to be higher. Right? So these are the characteristics of a differential pair. So by adding the current source, you will ensure that the biasing is proper. What does that mean? The Vs supply that you expect the tail current to have, that Vs and biasing you will take it. Now you look at this, how is the DC biasing happening? This is a condition for DC biasing these circuits. So the DC biasing of the differential pair is dependent upon what is the RD or the VDS value that you need, and this will also determine what is the output swing, right? Output swing will be given as drain current times RD. So we are taking care of the bias condition, the output condition, and then what are the input conditions that we have. So if you note, this we have still not spoken about the feedback part. So these are the things that you will consider in a MOS differential pair. Now, if you have to do the analysis, right? If you have to perform a little more in-depth analysis, then find out how does the gain get impacted. Okay, so the gain get impacted in a differential pair. Your input is going to be either it is V in plus minus V in minus, or in some other notations you will have V in 1 minus V in 2. Okay, then the output is going to be V out plus minus V out minus, or V out 1 minus V out 2. Now these are the inputs and the outputs. Now let us draw the differential pair signal along with the circuits, and you see how that is going to impact your circuit design. So I will call the bias current as ISS in the source degeneration. Input, let it be as V into V in 1. Output, I will call it as V out 1, V out 2, VDB, RD1, RD2. So this is your differential pair. Now that we know what is the input to the output difference, so we will do something called a voltage sweep. Okay, What is the voltage sweep? We will vary V in 1 minus V in 2 from what do you say? From your minimum voltage to maximum. Min voltage to maximum. Here, what is min? 0 volt or ground. Max is your VDD supply. Now let us look the conditions, observations, what we will get. First observation. When V in 1 is more negative than V in 2, meaning V in 1 is less than V in 2. What happens? So if V in 1 is negative than V in 2, V in 1 will turn off. Okay, V in 2 will turn on. So V in 1 turn off, what do you get? This is off. So all the current will flow through. This is bias. Only current will go through this device to the ground. Right? In that case, what do you get? ID2, whatever is flowing through drain current of it, will flow through ISS. Okay. Now, since that is going to ISS, what will be the voltage Vout1? No current flow. Vout1 will be whatever is VDD, you will see on Vout. Vout1 will be equal to VDD. Then what is Vout2? Vout2 will be VDD minus I times RD. So what is I? ISS here. So VDD minus RD2 times ISS. So that will be the output voltage. Okay. Now, second condition is if V in 1 is approximately equal to, or it is brought very close to V2. Okay, and by the way, this condition also applies for the other way around. Okay, what is other way around? If your V in 2 is greater than V in 1. So here V in 2 will be, V in 2 is, let me rewrite consistently. If your V in 1 is greater than V in 2, then V in 1 will turn on, V in 2 will turn off. So ID1 will now be ISS. In that case, Vout1 will be equal to VDD minus the current flow here. Right? You will see the current flow in the following. Current will flow through this. This will be off. So what do you get? Vout1 is VDD minus ISS RD. Vout2 will be equal to VDD. Right? These are the two input conditions. Now, if V in 1 are very close to V in 2, then instead of these two being completely off, they will gradually turn on. M1 will gradually turn on. Okay, and M2 will stay on, depending upon which one was higher first. So if V in 2 was already higher and V in 1 is slowly brought close to V in 2, then M1 will turn on gradually. M2 is already turned on. So what that will happen? You will particularly now see the currents, since both devices are on, so currents will flow this way and this way. Both currents will flow. How will flow? They will turn on depending upon what is the ratio of the two circuits or the two turn on voltages. Right? So ID1 and ID2 will then be non-zero circuits, but they are sum of these two will be equal to ISS. So what proportion of it will go depends upon what is the VGS present between V in and V2. So this will be directly proportional to VGS1 and VGS2. Depending upon whichever is larger, that will draw higher portion of the ID current, but the cumulative current will be the same. Got it here? Now, what will happen? In that case, VO2, which was higher, let me draw the supply graph. 0, 80, 0, this will be VO1. Okay, and in this case, VO1 is here. VDD minus ISRD. VO2 will be in this case. VO2. So if you observe, only the circuit which was on will have a lower voltage. Now in this case, what will happen? As the current flows through each other, assuming VO1 was on top. VO1 was on top and VO2 was below. Right? As the current, as M1 is gradually turns on, there is going to be a drop across IRD. So this VOT will start moving downwards, and VO2, which is already turned on, some amount of current is being drawn back, split between the arrow. So whatever is the current flowing here and drop here, that will store only move the circuit upwards. Right? And at one particular point, when both the currents flowing through both the branches are equal, you will see that both VO1 and VO2 will have the same voltage.